Welcome to the deep dive. Our mission is, as always, to take the source material you share, the research, the notes, and really distill it down into the core knowledge. Today, we are tackling something big in 3D computer vision, a model called Depth Anything 3, or DA3.
And this one is built on a pretty powerful idea, core conviction really, that true depth perception is the absolute foundation for how an AI can understand the physical world around it.
Which is a bit of a shift, isn't it? For years, 3D vision has felt so fragmented.
It has. I mean, you had these hyper-specialized tools. You'd have one model just for monocular depth, a totally different one for structure for motion, and yet another for multi-view stereo.
So you were always kind of stuck stitching different pipelines together if you wanted the full picture of a scene. It sounds messy.
That's the old way of thinking, and DA3 really challenges that. The goal here is, well, it's radical. A single unified model that can recover 3D structure from basically any visual input you give it.
Any input, so a single photo, a video.
A single photo, a video stream, multiple views of an object, and this is critical. It's designed to work whether you know the camera positions or not. It's meant to be the one general-purpose backbone for 3D geometry.
Okay, let's get into that, because the strategy they used seems counterintuitive for a goal that ambitious. They talk about a minimal modeling strategy, which sounds like they're actively avoiding complexity.
They are, and that pursuit of simplicity led them to two really profound insights. The first one has to do with the model's backbone, its core engine.
Right.
They found they didn't need to engineer some complex custom architecture just for depth. A single plane transformer was actually enough.
Just a standard transformer, not something purpose-built for 3D.
Not at all. They used a vanilla DINO encoder. DINO of 2 specifically. And this is so important because it lets the model inherit all the powerful generalized feature extraction that these huge models learn from massive data sets.
Well, so instead of building from the ground up, they're plugging in an existing expert on understanding images.
That's it. They outsourced the visual understanding part so DA3 could focus purely on the geometry.
But doesn't that create a risk? Using a general backbone that wasn't built for 3D specifically, you'd think you might lose some geometric precision.
You would, and that's where the second insight comes in. They paired it with a singular prediction target, something they called the depth ray representation. It's so effective, it just removes the need for all that complicated multitask learning you usually see.
Okay, that sounds like the core innovation then, the depth ray representation. What is the model actually predicting?
For every image you put in, it outputs two things, a depth map, which is pretty standard, and this special ray map, which they call $.
And that ray map is the key.
It's the geometric core. It's dense, so there's a value for every single pixel, and each pixel gets 6 numbers.
6 numbers. What do they represent in 3D space?
They represent 2 vectors. The first 3 numbers are the ray's origin point in space, and the next 3 are its direction. So for every pixel, the model is telling you, here's where this ray of light started, and here's the direction it was traveling.
And the real power is in the math that comes next, I'm guessing.
It is. I mean, historically, one of the biggest headaches in this field has been predicting a valid rotation matrix for the camera.
Because it has all those strict mathematical constraints, right?
It does. It's a huge computational and geometric mess to optimize for directly. The depth ray representation just sidesteps that entire problem. It never predicts a rotation matrix at all.
So how does it create a 3D point?
It's just simple algebra. A 3D point is the ray origin plus the depth value for that pixel multiplied by the ray's direction. That's it. It's all element-wise operations, which is incredibly efficient and avoids all that complex optimization.
That is clever. So that's the minimal modeling in action.
Yeah.
Now, what about the architecture that makes this happen? The backbone is DINO v2, but how does it handle multiple images at once?
They made a small but very effective change, an input adaptive cross-view self-attention mechanism.
Okay, what does that do?
When you feed it multiple views, it dynamically shuffles the image tokens around in certain layers of the transformer. It lets the model directly compare features from different viewpoints so it can reason about the 3D structure.
And they don't do this at every single layer, do they?
No, that would be too slow. They found an optimal rhythm. The model alternates. It'll do 2 layers of processing within each view, sort of internal thinking, and then 1 layer of this cross-view attention where it collaborates across all the views.
2 to 1. A balance between internal processing and global collaboration.
And that keeps the compute manageable. Then at the end, a novel dual DPT head takes over and generates the final depth and ray values.
Dual head. So it's forcing the 2 predictions to be generated together. from the same information.
They share a lot of the same modules right up until the final fusion stage. It encourages the depth and the pose information to be really consistent with each other.
And what about when you do have camera information? The model is supposed to handle both cases.
Right. If you have the camera poses, they get encoded by a small network into a special camera token. That token just gets added to the input sequence and participates in all the attention steps, acting like a geometric anchor.
And if you don't have them?
The model just uses a shared learnable token instead. So it essentially learns to infer the geometric context from the images alone.
Let's talk about training then. To make a generalist model like this work, you need a ton of data. But the sources point out that real-world depth data is, well, it's often a mess.
It's a huge problem. It can be noisy, sparse, incomplete. You can't just train on that and expect to learn fine details. That's why they needed a teacher-student learning paradigm.
Okay, so they build a teacher model first.
Yes. And this teacher is a monocular depth model that's trained only on a huge, expanded set of clean, perfect, synthetic data.
So the teacher understands ideal geometry, but it doesn't have that real-world grounding yet.
Not yet. The teacher's job is to look at all the messy real-world data and generate dense, high-quality pseudo-depth labels for it. But you can't just use those labels because they'd lose the geometric accuracy of the original sparse measurements.
You need to merge the best of both worlds, the detail from the synthetic teacher and the accuracy from the real-world sensors. How do they do that?
They use a robust alignment process. It's a ransack scale shift procedure.
Ransack. Random sample consensus.
Right. In simple terms, it finds the best way to scale and shift the teacher's dense, detailed map so that it aligns perfectly with the sparse but geometrically accurate real-world data points.
So you end up with a training label that has the detail of a perfect render, but the geometric truth of a real sensor.
And that's what the final DA3 student model learns from. It's a much richer, cleaner supervision signal.
And this all feeds into a final loss function, which has 5 parts. The expected ones are their depth, the ray map, the final 3D point map.
And then there's an optional one for the camera pose if you provide it. But there's also a gradient loss term, which is really important for quality.
What was that if?
It acts like a sharpener. It penalizes the model for blurring sharp edges like the corner of a room, while encouraging it to keep flat surfaces smooth. It preserves local detail.
So let's get to the results. They set up a whole new benchmark to test this, the visual geometry benchmark. What did it show for pose estimation?
The results were definitive. The biggest model, DA3 Giant, achieved state-of-the-art on basically every metric. It delivered at least an 8% relative improvement in accuracy over all competing methods.
An 8% jump is significant. And what about the actual 3D reconstruction quality?
Even more impressive, DA3 Giant show an average relative improvement of 25.1% over the previous best model, which was called VGGT.
25%. Now, that VGGT model was a huge, complex piece, wasn't it?
It was 1.19 billion parameters, and that's what makes this so remarkable.
So a model built on a minimal strategy is outperforming a complex model that's 3 times its size.
Not just that, even the smaller DA3 large variant, at only 0.36 billion parameters, still beat VGGT in multiple scenarios. It proves the power is in the representation and the training data, not just architectural brute force.
And beyond the benchmarks, they tested it on a real-world application, right? Novel view synthesis.
Yes, feed-forward novel view synthesis, or FFNVS. They just fine-tuned DA3 with one extra output head to generate parameters for 3D Gaussian splatting.
And the results.
2 key findings. First, a strong geometry model like DA3 used as a backbone consistently outperforms models that were specifically designed just for NVS.
So the generalist beats the specialist.
And the second finding ties it all together. They showed a direct correlation. The better the model's underlying geometric reconstruction capability, the better its performance on the final application. It established DA3 as the strongest backbone out there for this kind of task.
That's a powerful validation of their whole thesis then. It seems to prove that simplicity, when it's the right kind of simplicity, is more than enough for this unified approach to 3D vision. A single transformer with this depth ray target and the smart training process just works.
It really does. It redefines the starting point for anyone working on these problems.
So here's a final thought for you to take away. This research seems to prove that the bottleneck for many complex 3D applications isn't some fancy high-level reasoning. It's actually the raw quality of the foundational geometry estimation. So, if we can simplify and unify that core model, as DA3 has done, how might that democratize the entire field? Could it make things like sophisticated 3D scanning or robotic mapping accessible to everyone using just the hardware you already have? Something to think about. We appreciate you taking the deep dive with us.